That was where we left off. So let's summarize all of that on the next page here. Okay. We're trying to we're trying to quote unquote solve an inconsistent linear system. Okay. That doesn't make any sense, right? Because we know an inconsistent system has no solutions. So we're trying to approximate as best we can a solution to this system. Okay. So what we're trying to do is minimize that magnitude of ax minus b, making what we refer to as the error as small as possible. We did that by looking at the square of that and then realizing that that is as small as possible when we use the projection, right? When that ax is actually equal to the projection of b onto the subspace, okay? So that solution, the vector that we refer to when substituted to minimize that, is what we refer to as a least squares solution. And again, the reason why we call it least squares is because, again, we consider the square of that, put that adding and subtracting of the projection in there. Those were orthogonal, so we could split it up. And so we recognize that if we had the vector minus the projection, that was as small as we could possibly make the square, which is what minimizes that quantity. Okay. So we refer to that as a least square solution. Pardon me. To figure that out, that was when we called that normal system. We figured out, we rearranged that to create the normal system. And again, that normal system was A transpose A times X equals A transpose times B. That's what's referred to as the normal system. This is, notice, when you do your A transpose A, a couple of things you notice about it. One, it's square. When I do A transpose times A, I get a square matrix. It's also symmetric. So when you compute that, you should get a symmetric matrix as well. Okay. Again, we're trying to find, hopefully, a unique solution. This will always be consistent. Because, again, remember, we're using A. We're projecting B down into the column space of A. So when we write out the system, that's what we're doing. We're trying to project that down into the subspace that's generated by the columns. In particular, this vector over here will be in the column space of A transpose A. So it's always going to be consistent. Okay? You don't have to worry about it being inconsistent. We've created a consistent system because we're projecting down in the subspace that's generated by the columns. Okay, so we always get something that is consistent. It is solvable. Best case scenario is we get a unique solution, right? If I have a unique solution, that means I can take this matrix and invert it and put it on the other side. Okay? So we will get that unique solution provided that our A has n linearly independent columns. Okay. When we have n linearly independent columns, that tells us that this matrix will be invertible, and we can take the inverse on the other side. So the solution to this system will just be, you looking at that normal system, our solution will be A transpose A inverse times A transpose times B. That'll be the solution when we're done. That actually gives us the least square solution, which is what we're typically looking for, as we'll see in the next example. That's what we're typically looking for, is the least square solution. However, sometimes we might want to be able to figure out what the orthogonal projection onto the subspace is. Well, that's just going to be, I take my original matrix A and multiply it by that least square solution. Okay. Just plug it in. Just multiply that whole thing by A on the left and you get the projection. In particular, it's this formula that we're going to want to use to figure out a least square solution when we're given, say, data, all right? So let's do a couple of examples of that and see what's going on. You can do these in your calculator, but sometimes it's a little faster to plot these things and see the solutions and using, say, something like Excel to help. All right, so this is, we want to figure out what the least squares cubic polynomial is that best fits these 7 points. Notice that you're not going to get a you're not going to find a function that actually goes through all the 7 of those points. Why do I know that a function can't go through all 7 of those points? Looking at your points, how do I know a function is not going to work? In particular, look at your second and third points, look at your fifth and sixth points. How do I know a function is not going to work? I get two, yeah, plug in 0, I get 2 different answers, right? I plug in 2, I plug in 2 different answers, right? A function can't go through all those points because it won't pass the vertical line test, right? So right away, I know I'm not going to find any cubic or any other type of polynomial or any other type of function that will actually go through all 7 of those points, okay? So I'm going to try to get something that goes through, basically approximates those points as best as I can. And this problem is asking us to use a cubic polynomial to do that. All right. So remember that our general form of our cubic polynomial would look like some coefficients times x squared times x cubed, as well as the constant there, right? So basically I've got 4 unknowns to solve for. So I'm going to create a system to try to solve for those 4 unknowns. Now the system is going to end up with 7 equations. How do I know I'm going to get 7 equations? I've got 7 points, right? So I would set up a system of 7 equations with 4 unknowns. Well, that's more equations than unknowns, right? If I have 7 equations and 4 unknowns, we refer to that as overdetermined. And we know that overdetermined might give you too much information and make inconsistencies, right? Okay. So this is why we're going to use this inconsistent system and try to use the method of least squares to give us an approximate solution as best as we can. Okay. So if we set this up, yes. See, I was looking for a cubic polynomial. Okay. All right. So let's write down a couple of these equations and then see what's going on with them. So for example, your first equation, I have 7 for the output. I would have A, because there's nothing to plug in for x there, and then I'd have a minus B plus a C minus a D. That would be equation number 1, wouldn't it? The next equation, well, I'm gonna write it in, but I'll have 2 is equal to A, and then I'd have a 0B, a 0C, and a 0D, because it says to do 0 and 2, right? I'd have something similar for the next one. Let's do one that's a little bit more interesting. Let's look at the equation that would go with the 3 and the negative 18. There's 7 equations. I just want to see if we can figure out a pattern to this so that we're not having to write out the equations every single time. Okay? So if I look at the one with 3, on the left-hand side, I would have 18. On the right-hand side, I still have an A. In this case, I would have a 3B, a 9C, and a 27D, right? How am I getting those numbers? Well, I'm plugging in the x value for x, right? So I get a 3b, a 9c, a 27d. Again, I have 7 equations of 7 unknowns here, but what's the coefficient on the a every single time? 1. What's the coefficient on the b? The x, right? What's the coefficient on the c? X squared, and the one on the d is the x cubed, right? So if I go over to something like Excel, I can do this a little bit faster, assuming I have these things typed up here, or I can see them without having to flip back and forth. So if I go over to something like Excel, let me put the keyboard back on so I can actually type easily. All right, so we've got 7 points. I'm just going to type in the points to start with. I've got -1, bless you, 0, 0, 1, 2, 2, and 3. Those were the x coordinates. I've got outputs were 7, 2, 1, -2, -1, -2, and -18. Those were the points, right? So I've got the points entered. Okay. You just told me that the coefficient on the a every single time was 1, right? You also told me the coefficient on the b was just the x value. So I can just go over and I'm just going to recopy basically that column over. I'm just going to use the cell reference to do so. So I'm just going to have equals A1. The beauty of that is that I can copy that down, right? Okay. What was the next set of coefficients? It was the x value squared, right? So I can go back, grab the x value, square it, do the exact same thing, pull it down, right? It's a lot faster than typing it in the calculator, isn't it? Okay. The other one, I can grab that and cube it, right? Because it was the x value cubed. And again, grab it, pull it down. Okay. So that gives me the coefficient matrix. This is your A, right? Now remember the formula, I'm going to write it on the board so we don't forget what we need to do. When we do the least squares solution, again, that was A transpose A, do the inverse, multiply it by the A transpose, and then multiply it by the B, right? That's our solution, assuming we have n linearly independent columns, which we do here. We have 4 linearly independent columns, so my A transpose A will be invertible. Okay. You can check they're linearly independent, but they are. Okay. So this is my A. So the first thing I need to do is take the transpose, then multiply, then inverse, then multiply and multiply. Right? I got to do it step by step here. Okay. Good news is that Excel has functions for this. Okay. All right. So first, notice that there's a transpose function in Excel. Okay. So the way you use the transpose function is you just go and highlight the thing that use the transpose function and then go highlight what you want to take the transpose of. That's the matrix I want to take the transpose of. I go highlight it. I hit enter. It spits it out. Now it gives you a little thing here that says, your formula is filled. Yeah, no kidding. I got multiple cells here. The things that we're doing here in Excel are examples of what are referred to as array functions. You get an array of answers out. Okay. Rather than getting a single number out like you're used to with both functions in Excel, you get an array here of things. Okay. Yes, I understand. Thank you. All right. We took the transpose. What are you supposed to do with the transpose? Yes. No, all we're doing was the x's. Well, the y's that we're going to use here at the end. Yeah, okay. That's our b. Okay. The x's we use to get our coefficient matrix. All right, what do we want to do with the transpose? Multiply it by a, right? So the function in Excel to do matrix multiplication is m molt or molt. Okay. All right. 2 M's there. All right. So that's the function name for the matrix multiplication. I want to use the transpose, so I'll go highlight the transpose, and then a comma, and then go highlight the original matrix. Okay. One thing you might notice here is it's got a little hashtag behind that L1. This is just Excel understanding that what we highlighted here, these numbers are dependent upon that output of that array function. Usually when you do that block of things, it'll write it in this fashion like we have here. I'm using this as calculated values off of something else. That's why it looks different. Don't worry about it too much. Just make sure you all have it all highlighted. All right, so this will multiply the 2 matrices. What size matrix should we get when we're done? It should be a 4 by 4. Hey, look, there's a 4 by 4. Okay. All right, what do we do next? We took A transpose times A, the inverse. It's a matrix function, so it's minverse is what we want. M inverse. Okay. I want to take the inverse of this matrix here. Okay. That gives me that 4 by 4. We should be getting decimals here. That makes sense. Some of these we probably can interpret if we look at it. Those should be really 0, right? Does this tell it? Remember, this is scientific notation for 10 to the negative 16th. That's 0, essentially, right? Got little rounding errors going on when it's doing the function. But notice that you should get a symmetric matrix here. Notice this is symmetric, right? Symmetric around the base diagonal. So is the inverse. Okay. What do we want to take the inverse times? Yeah, the A transpose, right? So here's the inverse. And I want to multiply that by the transpose, which is over here. All right, I want to multiply those 2 things together. Okay. And then finally, I don't see it. I'm going to copy them back down so I can see it. But we want to take that matrix and multiply by the B, the outputs, right? Okay. So I'll do the matrix multiply, matrix multiply again of this that big long thing there times the outputs, which are back over here. Since I'm zoomed in, it's a little harder to see. Let me zoom in out just a little bit. Okay, so my outputs were up over here in the B column. I just multiplied that times the B column. And I got those. So those are now our coefficients, right? This should be the constant. This should be the coefficient on x, x squared, and x cubed. Okay, so we found our least squared cubic. Let's see that that actually works. Okay. One of the nice things I discovered is that if I copy this table over and go to something like Desmos and paste, it pastes the table for me. Oops. And makes a nice set of points for me. Right? So I've got some nice points in there. Okay. I want to put in that least squares cubic. So rather than having to flip-flop back and forth every time, I'm just going to copy and paste that over into Desmos as well. Notice that if I had that single column, it just made it a list, so I can edit this pretty quickly. That was my constant. This is my x coefficient. This is my x squared coefficient. And this is my x cubed. There we go. And there's your least squares cubic. That goes through those, or it tries to approximate those points. Okay. Obviously, again, we already mentioned that I'm not going to get a function that actually makes it through all those points, right? But this is the best cubic you can use and get through those points. Process on these is exactly the same every single time with these with polynomials in particular. Okay. What questions do you have? We'll do another one. Is okay? You can apply this technique to other types of functions so long as you can create a linear system. Okay? So going back to the next problem here, the coefficient on the B, the D, sorry. The get back over there. On the D was the negative 1.58333. Sorry. Yeah, so you can round it out whatever on the paper, you can do that. This I just copied and pasted over so it kept as many decimal places as possible. Okay. Yeah. Which, say that again? Oh, the way we set it up was this way, right? So the first one's A, the second one's B, the third one's C, and the last one's D. Yeah. All right. Let's go to the next one. When in spring 2020, I was teaching linear algebra. Spring 2020 came and messed up a lot of things, right? Right. So, well, this is actual case data from the U.S. with the coronavirus back in 2020. I emailed this data to you right before class if you want to play with it later, so you can play with Excel. It's a nice play with it. What I'm interested in, though, is how do we use this least squares method to fit this data using an exponential function? Why might I want an exponential function? Well, let me do this exact same thing I just did a minute ago with Desmos and plot the points. So go back over to Desmos and let's clear this off here. I'm going to go grab the points. I already got them typed into Excel here. Let's go back and plot these points. There we go. That looks like an exponential function, doesn't it? Okay. Exponential growth here, it's good, especially in the early stages of a disease breakout, to try to model what's going on, right? And then again, of course, during that time, we were trying to do mitigation techniques to try to get this to level off, right? It was one of the first things they did, right? So they closed everything, they didn't really wear masks, all that good stuff, right? Trying to get this to level off. All right, so we're just going to try to model this with an exponential function. Now, what we've done so far, everything's been a linear system, right? And if I'm going to do this, I need to be able to convert this to a linear system. Okay? What function do you know changes products into sums? What function do you know changes products into sums? Natural log does, right? Let's take the natural log of both sides of this equation. If I take the natural log of this, I would have natural log of y equals natural log of a plus b times x, right? I have a product of a times b, or e to the bx. Natural log of a product is the sum of the logs, and then natural log and e cancel each other out, don't they? They're inverses of each other. Okay. Now I've created a new linear system, right? Notice in this case, I can think about this as being some other variable. I'll call it z to start with. And then some other constant, I'll just call it a c plus bx, right? I've converted it to a linear system, haven't I? Okay. But notice that for my outputs here, I need to take the log of that y, don't I? To start. You see how I've created a linear system here? Okay. So let's go back over to Excel and use, I don't know why I took that off. Let's go back over to Excel and use that information. All right. So first thing I want to do is I'm going to take the log of each of these, each of those outputs. Okay. The command for log in Excel, oops, we went too far. The command for log in Excel is just ln, just like it is on your calculator. All right. Again, the reason why I took the natural log, I don't know why I keep writing a B there. The reason why I took the natural log of each of the outputs is because notice that when we changed our system to a linear one, it says do the logs of the y's, right? The logs of the outputs. Okay? So that's why I took the log. This is my B vector now that I'm going to use. Okay? All right. Again, if I form my linear system, I'm gonna find this C now that I have, right? I'm just saying, think of that as just a constant C, and I'll find this B. What's the coefficient on the C going to be for all of those numbers? No matter what we plug in for X, what's the coefficient on the C always going to be? Okay, let me ask you a different question. How many equations are we going to set up in this case? 27, because I got 27 data points, right? But for every single X we plug in and Y we're supposed, or Z we're supposed to get out, what's the coefficient on the C in all 27 of the equations? 1, right? Because no matter what I plug in for X, I get a C plus something times X, right? So my coefficient on my C is still a 1. That constant's all going to be 1s, because that's the coefficient on the C. What's the coefficient on the X? Or excuse me, what's the coefficient on the B? So is that the input or the output? Or the 69, 89, and so on, is that the input or the output? That's the output. So what input is associated with each of those? The day, yeah. So 1, 2, or I can just do, like we did before, I can just say it's equal to the X value over here, right? Notice we get a 27 by 2 matrix in this case, right? What do I want to do? That's our coefficient matrix now. What do we do with that? Transpose it. So we'll take the transpose. After we take the transpose, what do we do? Multiply. Yep. And multiply by A transpose, which is way over here. We'll scroll back over because it's too big on the screen here. Times my A. We got a 2 by 2 in that case, a little bit smaller, right? What do we do with that? Inverse. Use the right inverse command. Minverse. What do we do with that? Yeah, multiply by the transpose. So that times this big long thing. And then finally, what do we multiply that by? The outputs, right? The outputs that we want to model. Now remember that my outputs, we had to take the log first, right? So I want to do this one with it, what we did with all the logs here. Okay. Notice I'm not using the case data. I'm using the log of the case data. We had to take the log first to convert it to a linear, right? Okay. So at this point now, if I hit enter, that 3.77 is this C value. The 0.2849 is this B value here. Okay. Now, are those the values that I want? Well, this B does correspond to the correct B here. But is C the right value for A? Is C the same thing as A? What do we let C equal? A log of A, right? How do I get A from this? How do we get A from the C value we just found? E to the C, yeah, good. So I'll do E to the value for C we just found. Okay. I have to undo the natural log that's here, right? Remember? This corresponded to that. That corresponded to that, didn't it? But we want A, not log of A, right? So I have to undo it. All right. So if I use this 43.58783, let's go back over to Desmos. Maybe. Let's go. There we go. And then E, let me delete that out. Whoops. And then we did E to the 284949 times X. There we get our model of our data with an exponential function. Okay. Again, remember the B stayed, right? I didn't have to change my B, but my A, when we converted to a linear system, I had to undo it. That's why I had to do E to that power. And then you can see how we get a model, and this is how this stuff is done. I mean, honestly, how this stuff is done is you put it in a computer program and spit it all out. I'm showing you where it's coming from. All right. What questions do you have on? Yes?
You said we just do it each part. Why did we apply something at the front?
Say that again?
Why did we apply something at the front when you said CS?
The C is the natural log of the constant in front. This became that when I took the natural log of both sides. Okay, so I did with a C that we found using the least squares method is the log of the constant in front. I have to undo that to get the constant. The E is undoing the natural log that we took to start with. Okay, we found the C was about 3.77, right? Okay, that's equal to natural log of A, the constant that's in front. I have to do E to both sides to get that 43. Whatever the number is. That's why I had to undo it to get that value. All right. Again, we use that just to convert what was going on to a linear system. Once you get to a linear system, the process is the same every single time. Set up your coefficient matrix, take its transpose, take that times the coefficient matrix, do the inverse, take it times the transpose, take your output vector. The process is the same every single time. The trick is to get it into that form. Now, in the first case, we didn't have to do a lot of work to get in that form, right? Because we had everything was a nice matrix, right? A nice linear system of coefficients. This wouldn't be a linear system to start with. That's why we took the log first to convert it into a linear system. Other questions on that one before we switch gears slightly? Not too bad. All right. So this works nicely when you have a set of data and you're trying to fit a function to the data, okay? But sometimes you have a function that you want to try to approximate. specific example, your calculators, all they know how to do is switch switches on and off. That's all a calculator or a computer knows how to do. Something's on, something's off. Something's on, something's off. Using something on and something off, you can define addition, you can define subtraction, multiplication, division, all of those nice things. Anything that might have to do with a polynomial, you can define nicely. But once you start trying to do e to the x or sine x or cosine of x, the calculators can't do that anymore. So you have to have really good approximations of those functions with polynomials. Okay. So that's an actual practical idea of why we want to do the following thing. Now we're going to approximate kind of nastier functions with trig polynomials. So something that's repetitive. So for example, maybe something turns on and then turns back off, and then turns back on and turns back off. Okay. That's a piecewise defined function. It's constant for a while, you turn it off, and then it's constant for a while, you turn it back on, it's constant for a while, and so on down the line. Okay. So we use what's referred to as Fourier series to approximate repetitive functions, because trig functions, sine and cosine, have period 2 pi. So if we have something that's repetitive, we can use sines and cosines to model that repetitiveness. All right, before we get there, let's remind ourselves of how we do projection if we have an orthonormal basis. Remember how we did projection with orthonormal bases? What did we need to do? Oops. How can we do if we know that this is an orthonormal basis to start with? How can you do projections? What do you do? Yeah, you do dot products, right? You take your V dotted with W1 and then multiply it by W1, right? And then do the same thing with your W2 and all the way through until you're done. And this works for any inner product. Doesn't have to be Euclidean. So we can use this principle to do projections onto a subspace with function spaces. Okay? So we're going to start with a subspace of the continuous functions on the interval from 0 to 2 pi. That's generated by a constant function. There should be, if I'm going to have that in there should be a 3 in there. I didn't even mean to put that function in there. There should be a 3 in there. All right, so we're going to do a constant. We're going to do a cosine of just a single, cosine of 1x, cosine of 2x, cosine of 3x, and so on to cosine of nx. And then sine of x, sine of 2x, all the way out to sine of nx. Okay? So we're going to do linear, I'll talk about the constant in a second, in a second. We're going to do linear combinations of sines of some coefficient times x and cosines of some coefficient times x. We refer to those as trig polynomials, even though we don't square or cube. The constants are on the inside. We call those trig polynomials. Okay? So this subspace is just generated by, in some sense, nth degree, it's not really degree, but nth degree trig polynomials. Okay? We've got n sine functions and we have n cosine functions in the constant term. Okay? That's what this is generated by. All right. So why do I have these constants out in front? But before I do the constants out in front, what you can show is that if I do the inner product, remember our inner product for continuous function spaces is an integral of a product? When we're doing those for inner products? Okay? We can show that if I take any distinct ones, that inner product will be 0. Okay? not worrying about the coefficients out in front. But if I take, say, a cosine of x and multiply it by a sine of 2x, I'll get 0. Right? If I take a cosine of 5x and multiply it by a cosine of 7x, I get 0 for the integral. You can show that they really are orthogonal to each other. Okay? So if I ignore those 1 over root pi's and that 1 over root 2 pi, I've got an orthogonal basis. Those constants out in front are dividing by their magnitudes, and so I could rate it an orthonormal basis. Okay? Without going through all the work, if you want to see all the work, I'm happy to show it to you outside of class. But this really does form an orthonormal basis. Okay? So using this, we can create a projection of any other function that I want and approximate it with these trig polynomials. So how do we do that? Well, let's say we have the function just x on the interval from 0 to 2 pi. Okay. You told me a minute ago to find projection onto a subspace. I just need to take the inner product of whatever the inner product of the vector with each of the basis vectors, right? Okay. So I'm going to take the inner product of x with each of these basis vectors that we have, okay, in this particular example. But in general, you would do whatever the function is and do the inner product with the constant. And whatever the function is, an inner product with each of the cosines, and whatever the function is in the inner product with each of the sines. Okay, so that's what these notations are. Your a sub 0 is your inner product of the function with the constant term here. So I'm just going to put the 1 over root 2 pi out in front. Okay. That's what the a sub 0 is. So in this particular example, for the x, your a sub 0 would be 1 over root 2 pi, integral from 0 to 2 pi of just x dx. Okay? Yes? Yes. And we're doing the inner product of the f with each of those vectors. So yes, it was replacing the g of x. Okay, so that's what the a naught is. It's your constant term for your Fourier series. Okay. Notice it's the a naught here, right? So we're doing the inner product of the function with the constant. Okay. Your a's, your other a's, are your inner product of the f with the cosines. Okay. So whatever the a sub I is, whatever the I is, it's going to be 1 over root pi integral from 0 to 2 pi of f of x, not sine, I just said it was cosine, cosine of ix, whatever. I is probably a bad letter. I probably should have used an n, but it's fine, dx. It's not the imaginary unit. It literally is just a counter here. It's an index. Okay. So your a's are your integral of the function times the cosines. Okay. So in this particular example, your a sub I would be 1 over root pi integral from 0 to 2 pi of x cosine of whatever the I is, dx. Well, if I used cosine for the a, what do you think I'm going to use for the b? Sine, yeah, good. So you get 1 over root pi integral from 0 to 2 pi f of x sine of ix dx. In this particular example, I would have x sine of ix dx. So to get your coefficients, you would need to compute these integrals. Okay. These are not horrendous to do by hand in this particular case, but they might be a little bit more complicated to do by hand generally. So, in general, or in practice, maybe is a better word, you're going to go to a computer system to help you with this, right? I would go to something like GeoGebra because it's free. I would also switch this over to a computer algebra system just to help us out, because I want to try to do this in general if I can. So our integral that we'll want to do, let's say we did the cosines. I'm not going to worry about the coefficient here in a second. I want to worry about doing the x and the cosine. So it was x times cosine of, I'm going to use an n this time just to make myself feel a little bit better. The n or the I that we wrote down was just your index. I'll use an n here. I want to integrate that function with respect to x. I want to start at 0 and I want to end at 2 times pi, right? Okay. One little quirk of GeoGebra, and we'll do more of this on Monday as well. One little quirk of GeoGebra is you want to make sure you put a space in to denote multiplication. Don't just write nx, because it'll treat nx as a whole variable, not n times x. Okay. All right. It'll give you a nice formula with n's in it, okay? But we should be able to simplify this a little bit if we think about it. Okay? I know I'm out of time. What's sine of 2n pi going to be all the time? If I do a multiple of 2 pi and take the sine of it, what do you always get? 0. Good. That whole term goes away, right? Agree? Now, no, GeoGebra doesn't know that because it's just treating n as a letter, right? But we know that this n is representing an integer, so that goes away. What's cosine of 2 multiple of 2 pi always equal to? 1, right? So this big fraction here simplifies to 1 over n squared, but I've got a minus 1 over n squared. What do I get? 0 all the time, right? So that your a's, all your a's are 0 here, right? Except for the a naught. We have to do that one separately. But all the a's are 0, okay? You would do the same thing for the b's, and we'll do that next time and finish this off, and we'll do a couple more examples of that as well. I do have some homework problems if you want to use for practice or what have you, or least square stuff. But we'll finish this off next time and do another example or two. Make sure we got it. This is a very computer active idea, by the way. I'm not expecting you to do these by hand by any stretch of the imagination. All right. Have a good one. We'll see you on Monday. Remember, no class Friday because it's Good Friday. So I'll see you on Monday. All right. Have a good one.